According to this theory, our universe is just one among an infinite ensemble of parallel universes. Each universe within this vast ensemble may have different properties, leading to a staggering array of diverse realities. Every conceivable outcome and configuration exists, encompassing an unimaginable breadth of cosmic landscapes. From universes where the laws of physics are entirely different to those where life takes on forms we can scarcely imagine. Strange, right? The next one, Theory 4, suggests that the reality we perceive as the universe is, in fact, a sophisticated program created by an advanced civilization or a higher intelligence. In this scenario, our entire existence, including the laws of physics, the fundamental particles, and even our own consciousness, is a product of an intricately designed computer program. It proposes that what we perceive as the physical world is a complex virtual construct, akin to some sort of hyper-advanced video game. Supporters of this theory argue that the rapid advancements in technology and computing power, along with our own efforts to create realistic virtual environments, point towards the feasibility of such a universe. They propose.
With the Maui column line array PAs from LD Systems, you can set up in seconds and fill any space with powerful sound. They're compact, lightweight, and occupy almost no space on a stage or dance floor. Shop Maui PAs at Sweetwater.
That an advanced civilization with incomprehensible computing capabilities could create a simulated reality that is indistinguishable from the real universe. Well, I've given you about 4 theories. If you know the names of these theories, make sure you comment their names below. Let's continue. You see, the universe is very strange. We've got particles popping in and popping out of existence everywhere. There's something, and then pop, nothing. We've got dark matter, a mysterious substance that makes up a significant portion of the universe's mass, but remains invisible to our current methods of observation. It does not emit, absorb, or reflect light, yet its gravitational effects can be observed in galaxies and the large-scale structure of the universe. We've also got dark energy, which seems to be expanding the universe with immense speed. Unlike gravity, which acts as an attractive force, dark energy seems to push galaxies apart, causing the fabric of space itself to stretch. This expansion occurs on such a grand scale that it surpasses the gravitational forces between galaxies, leading to an ever-widening cosmic expanse. And then we have the Big Bang, which tries to explain the origin and evolution of our universe. That the universe as we know it began from an incredibly hot and dense state approximately 13.8 billion years ago, suggesting that all matter, energy, space, and time originated from a singularity, a point of infinite density and temperature. In an extraordinary event, the universe rapidly expanded and continues to expand to this day. It was during this expansion that the fundamental forces and particles that govern the cosmos came into existence. But is it perfect? Did the Big Bang happen inside space, or was the Big Bang the beginning of space itself? Where did it happen, and how did it happen? Why did it happen in the first place? You see, the Big Bang Theory gives us a remarkable glimpse into the birth of our universe, but there are still many unanswered questions. We may have an idea of what happened after the bang, but what happened before the bang is where we are left hanging. How could all matter, energy, space, and time be packed into a point of infinite density and temperature? It boggles the mind. Strangely enough, some cosmologists entertain the idea that a previous incarnation of emptiness, a cold, dark, and empty universe, similar to the one awaiting us in the distant future, could have been the source of our very own Big Bang. This may sound confusing, but let me explain what I mean. First off, I want us to look at how the concept of material or physical matter came into existence. When we consider the origins of stable matter composed of atoms or molecules, it becomes clear that such matter did not exist during the initial stages of the Big Bang, nor for hundreds of thousands of years thereafter. The early universe was a hot and dense environment, filled with highly energetic particles that prevented the formation of complex matter. However, as the universe expanded and cooled over time, conditions became favorable for the formation of the first atoms. This process, known as nucleosynthesis, allowed simpler particles to combine and create stable atoms such as hydrogen and helium. But this understanding doesn't address the question of whether something came from nothing. Going further back in time, around 1/10,000th of a second after the Big Bang, the first long-lived matter particles, namely protons and neutrons, emerged. These particles form the building blocks of atomic nuclei. Prior to this crucial moment, there wasn't any material as we commonly understand it. But physics lets us keep on tracing the timeline backward to physical processes which predate any stable matter. This brings us to the fascinating era known as the Grand Unified Epoch. At this stage, we delve into the realm of speculative physics since our current experiments cannot generate enough energy to directly observe the processes that occurred during that time. Nonetheless, there is a plausible hypothesis that the physical world consisted of a swirling mixture of short-lived elementary particles, including quarks, which are the fundamental constituents of protons and neutrons. During this epoch, there existed both matter and its antimatter counterpart in roughly equal amounts. Each matter particle, such as a quark, had its antimatter counterpart, which was almost identical but differed in one aspect. However, whenever matter and antimatter encountered one another, they would instantaneously annihilate, transforming into pure energy. As a result, these particles were constantly being created and destroyed, a vibrant dance of matter and antimatter. But how did these particles come into existence in the first place? According to quantum field theory, even a seemingly empty vacuum, which corresponds to empty space-time, is teeming with dynamic energy fluctuations. These fluctuations have the potential to give rise to particles spontaneously appearing, only to vanish shortly thereafter. At first glance, this might seem like a peculiar mathematical phenomenon, rather than something grounded in physical reality. However, the existence of such particles has been observed in numerous experiments, providing tangible evidence of their fleeting existence. The space-time vacuum state is a bustling realm where particles are continuously being created and annihilated, seemingly emerging out of nothing. However, this observation leads us to consider that the quantum vacuum, despite its name, is not an empty void, but rather a dynamic entity in its own right. This notion challenges the idea of getting something from nothing. Suppose we ask the question, where did space-time itself arise from? We find ourselves delving deeper into the distant past, reaching the ancient Planck epoch, a period so early in the universe's history that our best theories of physics break down. This era occurred only 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second after the Big Bang. At this point, space and time themselves became subject to quantum fluctuations. Physicists ordinarily work separately with quantum mechanics, which rules the microworld of particles, and with general relativity, which applies on large cosmic scales. But to truly understand the Planck epoch, we need a complete theory of quantum gravity, merging the two. While we have yet to achieve a definitive theory of quantum gravity, scientists have made notable attempts through frameworks such as string theory and loop quantum gravity. Within these approaches, the conventional notions of space and time undergo a transformation. They are perceived as emergent phenomena, analogous to the rippling waves that manifest on the surface of a vast ocean. According to these theories, our familiar experience of space and time arises from underlying quantum processes occurring at a minuscule microscopic level. These processes, operating beyond our intuitive grasp as beings entrenched in the macroscopic world, present intriguing challenges to our understanding. In the Planck epoch, our ordinary understanding of space and time breaks down, so we can't even rely on our ordinary understanding of cause and effect either. Despite this, all candidate theories of quantum gravity describe something physical that was going on in the Planck epoch, some quantum precursor of ordinary space and time. But where did all of that come from? Even if causality no longer applies in any ordinary fashion, it might still be possible to explain one component of the Planck epoch universe in terms of another. Unfortunately, by now even our best physics fails completely to provide answers. Until we make further progress toward a theory of everything, we won't be able to give any definitive answer. The most we can say with confidence at this stage is that physics has so far found no confirmed instances of something arising from nothing. To truly answer the question of how something could arise from nothing, we would need to explain the quantum state of the entire universe at the beginning of the Planck epoch. All attempts to do this remain highly speculative. In 2020, renowned physicist Roger Penrose, a recipient of the Nobel Prize, introduced an intriguing yet controversial concept known as conformal cyclic cosmology to describe a cyclical universe. A cyclical universe is a model of cosmic evolution according to which the universe undergoes endless cycles of expansion and cooling, each beginning with a big bang and ending in a big crunch. Penrose was motivated by a fascinating mathematical relationship between the hot, dense, and small state of the universe during the Big Bang and the cold, expanded, and empty state it is predicted to reach in the distant future. His radical theory proposes that these states become mathematically identical when taken to their extreme limits. This paradoxical notion suggests that the complete absence of matter could potentially give rise to all the matter that exists in our observable universe today. In this perspective, the Big Bang emerges from what can be considered as almost nothing. This notion arises when all the matter within a universe is gradually absorbed by black holes, which eventually dissipate into photons and vanish into a vast void. Thus, the entire universe originates from a state that, when observed from an alternative physical standpoint, closely resembles absolute nothingness. However, even within this apparent nothingness, there exists a particular kind of something. It is still a physical universe, albeit one that is remarkably empty and devoid of traditional matter. How can the very same state be a cold, empty universe from one perspective and a hot, dense universe from another? The answer lies in a complex mathematical procedure called conformal rescaling, a geometrical transformation which in effect alters the size of an object but leaves its shape unchanged. Penrose demonstrated how the cold, dense state and the hot, dense state could be connected through this rescaling process, aligning their space-time shapes while disregarding their sizes. It can be challenging to comprehend how two objects can be considered identical when they have different sizes, but Penrose suggests that size loses its conventional meaning in these extraordinary physical environments. The focus shifts towards understanding the fundamental nature of the spacetimes and the underlying connections between them, transcending the constraints of size as we typically perceive it. In conformal cyclic cosmology, the explanation unfolds in a unique manner, from the old and cold state to the young and hot state. The existence of the hot, dense state is attributed to the cold, empty state, but this because is not the usual cause and effect relationship we are familiar with, where one event follows another in time. In these extreme states, not only does size lose its significance, but so does time. The cold, dense state and the hot, dense state exist on different timelines, separated by their distinct temporal geometries. From the perspective of an observer within the cold, empty state, it would persist indefinitely in its own timeline. However, the hot, dense state that emerges creates a new timeline entirely, with its own distinct properties and evolution. It may help to understand the hot, dense state as produced from the cold, empty state in some non-causal way. Perhaps we should say that the hot, dense state emerges from, or is grounded in, or realized by the cold, empty state. These are distinctively metaphysical ideas which have been explored by philosophers of science extensively, especially in the context of quantum gravity, where ordinary cause and effect seem to break down. At the limits of our knowledge, physics and philosophy become hard to disentangle. Conformal cyclic cosmology provides us with intriguing and speculative insights into the origins of our Big Bang. However, even if Penrose's ideas are confirmed by future advancements in cosmology, we may find ourselves confronted with a deeper philosophical inquiry. This inquiry revolves around the origin of physical reality itself and raises the fundamental question of how the entire system of cycles came into existence. Ultimately, we are led to ponder one of the most profound questions in metaphysics. Why is there something rather than nothing? This question delves into the very nature of existence and challenges us to explore the mysteries of our reality at its most fundamental level. But our focus here is on explanations that remain within the realm of physics. There are three broad options to the deeper question of how the cycles began. It could have no physical explanation at all, or there could be endlessly repeating cycles, each a universe in its own right, with the initial quantum state of each universe explained by some feature of the universe before. Or there could be one single cycle, and one single repeating universe, with the beginning of that cycle explained by some feature of its own end. The latter two approaches avoid the need for any uncaused events, and this gives them a distinctive appeal. Nothing would be left unexplained by physics. Penrose envisions a continuous sequence of new cycles, driven in part by his interpretation of quantum theory. In quantum mechanics, a physical system exists in a superposition of multiple states simultaneously, and only resolves into a specific state upon measurement. According to Penrose, each cycle involves random quantum events unfolding in unique ways, resulting in variations between cycles. This concept holds promise for experimental physicists, as it suggests the possibility of detecting remnants or anomalies from the previous universe that gave birth to our own. By studying the faint traces in the residual radiation from the Big Bang, observed by satellites like Planck, we may gain insights into the ancient universe that preceded ours. Penrose and his collaborators believe they may have spotted these traces already, attributing patterns in the Planck data to radiation from supermassive black holes in the previous universe. However, their claimed observations have been challenged by other physicists, and the jury remains out. Endless new cycles are key to Penrose's own vision. But there is a natural way to convert conformal cyclic cosmology from a multi-cycle to a one-cycle form. Then physical reality consists of a single cycle around through the Big Bang to a maximally empty state in the far future, and then around again to the very same Big Bang, giving rise to the very same universe all over again. This notion aligns with an alternative understanding of quantum mechanics called the many worlds interpretation. According to this interpretation, when we measure a system in a superposition, the result we observe is not a random selection. Instead, it represents just one possibility that unfolds in our own universe. In the many worlds interpretation, each of the other measurement outcomes plays out in separate parallel universes within a vast multiverse, entirely disconnected from our own. Therefore, no matter how improbable an event may be, if it has a non-zero probability, it occurs in some quantum parallel world. In these other worlds, there are individuals similar to you who have won the lottery, been caught up in unusual typhoons, spontaneously combusted, or even experienced all three events simultaneously. Our Big Bang might be the rebirth of one single quantum multiverse, containing infinitely many different universes all occurring together. According to some theories, parallel universes could leave traces in the data we observe from the cosmos, such as signs of collisions between our universe and others. This idea connects with the concept of many worlds quantum theory, although not everyone agrees, including Penrose. In this view, our Big Bang could mark the beginning of a vast quantum multiverse where countless universes coexist simultaneously. In this multiverse, every possible event and outcome takes place, repeating endlessly in a cycle of existence. It suggests that everything imaginable not only happens once but occurs repeatedly, creating a rich tapestry of infinite universes. Okay, to understand how the universe came from nothing, we need to delve into its nature. Our universe operates in two fundamental ways, which shape the fabric of reality and provide insights into its origins. The first mode is the deterministic nature of the universe. Determinism suggests that every event and outcome in the universe is governed by a set of predetermined conditions and the laws of nature. This viewpoint posits that if we possess complete knowledge of the initial state of the universe and the governing laws, we can predict the future trajectory of events with certainty. Determinism provides a sense of order and predictability, offering a foundation for scientific inquiry and understanding. However, as we explore deeper into the mysteries of the universe, we encounter the second mode of operation, the probabilistic nature of the universe. This aspect, prominently observed in the realm of quantum mechanics, introduces inherent randomness and uncertainty into the fabric of reality. At the subatomic level, particles and their properties exhibit probabilistic behavior, where outcomes are expressed as probabilities rather than definite predictions. This probabilistic nature challenges the strict determinism of classical physics and brings to light the fascinating realm of quantum indeterminacy. The interplay between determinism and probability raises profound questions about the nature of the universe and its origins. How do these two modes coexist? Can determinism fully explain the complex emergence of our universe from nothingness, or does the probabilistic nature of quantum mechanics play a role? Exploring these questions allows us to peer into the fundamental nature of reality itself. Determinism, as we have discussed, proposes that every event and outcome in the universe is predetermined by a set of initial conditions and the laws of nature. In the context of the universe coming from nothing, determinism provides a framework for exploring the sequence of events that could have led to its existence. At the earliest moments of the universe, we imagine a state of absolute nothingness. In this hypothetical scenario, there is no matter, energy, or even space and time as we know them. However, according to determinism, there must have been a specific set of initial conditions that set the stage for the universe's emergence. These initial conditions could involve various factors, such as the properties of the singularity, the values of fundamental constants, or even the existence of additional dimensions beyond our current understanding. The exact nature of these initial conditions is still a subject of intense scientific investigation and speculation. According to determinism, the evolution of the universe is governed by the laws of physics, such as general relativity and quantum mechanics. These laws dictate how matter, energy, and space-time interact and evolve over time. By understanding these laws and the initial conditions that set the stage for the universe's existence, we can trace the sequence of events that led to its formation. As the universe expands, matter and energy undergo various transformations and interactions. Particles emerge, forces come into play, and structures begin to form. Through the interplay of gravity, electromagnetism, and the strong and weak nuclear forces, galaxies, stars, and planets take shape over vast cosmic timescales. Determinism allows us to conceive of this cosmic symphony as a deterministic process, where each stage of the universe's evolution is